Okay, so Vijay will continue where he left off yesterday, and with much tenacity, he's going to take us between odd and even levels and talk about petals and blossoms and the guts and bones of his algorithm.
Okay, so welcome back. And as I said yesterday, feel free to stop me any number of times, ask me any questions. Okay, and so this is part two. So just to recap one or two things. So we are executing a phase in order m time, right? By the way, we have Jack Edmonds' wife, Kathy Cameron, here. So an honor, because this is a follow-up on Jack's work. So in a phase, we are going to find a maximal set of disjoint minimum length augmenting paths with respect to the current matching, augment the matching, and go on, right? And we're going to try to do this in order m time. And we defined, so by spending order 1 time per edge on most things, but then there'll be some data structures that need sort of amortized order m time also. I had defined the even level and odd level of vertices to be the length of the shortest even alternating path from an unmatched vertex to V or an shortest odd path, infinity if there's no such path, and min level and max level to be the smaller or the larger of these two levels. And min level and max level were found in qualitatively different ways. And that's all coming up very soon in the summary of the algorithm, which will come up. And the last time I left you with this picture, which is the main concepts. So they are all held together by the notion of tenacity. I defined the tenacity of vertices, but I'll define it again. And now I'll also define tenacities of edges and use these notions to define first tell you what the role of the bridge is, then tell you how to define base, and using that how to define blossoms and what role base and blossom play and what role bridges play. Okay, and these are purely graph theoretic definitions. And why did I have to go to that level of detail to define graph theoretically everything, which makes it much harder? I'll also justify that. Okay, so this was also defined yesterday, that a prop, any edge UV such that one endpoint is a predecessor of the other is called a prop. And if so, U assigns V its min level. So props assign min levels. All other edges in the graph are called bridges, and some of them assign max levels, some of them are vacuous. We'll see examples. Most of them will be vacuous in the end, but in the pictures that I draw, most of them will be useful. Okay, and these bridges assign max levels via double depth search, which is a new search procedure that you saw yesterday. Okay, so in this picture, this is a bridge, and all other edges are props because they give min levels. Like this edge gives this guy one min level of 1, this guy 2, these two 3 to these guys, and these two 4 to these guys. And this guy doesn't give min level to either endpoint because they get their min levels from some other places. So this is a bridge, and it assigns max levels because then the 4 from 4 you search and notice that this is 5. From 5 you can search and notice that this is 6. But you cannot go down and assign a finite odd level to this because this is a self-intersecting path. And you cannot just let search to go around and come around like this and start giving wrong max levels to these vertices. That's the whole reason to just define a blossom and curtail search right here and define max level for only these 4 vertices, which are the vertices in this blossom. Okay, so that's the role of the blossom, to assign max levels to just the right set of vertices. Okay, and I defined the tenacity of a vertex to be the sum of the even and the odd levels. And you can think of a small lollipop here, which has length 9, because it is 1, 2, 3, 4, 5, 6, 7, 8, 9. And that's the tenacity of these 4 vertices. They all sit inside the same lollipop. Okay, and here the tenacity of the green vertices is 13. There's a small lollipop here, and the purple ones is 15, and the yellow ones is 17, and the white one is infinity. It has no odd level. No, odd level is infinite. Okay? So then one more thing to notice is that all these edges, these 5 edges, are also sitting inside a lollipop of length 9. So I should define the notion of a tenacity of an edge also. Okay, and I'll define it like this. So all these edges will turn out to have tenacity 9. And what's the correct definition there? So if an edge is unmatched, then you take the even level of u plus the even level of v plus 1. So that completes the lollipop. It has to be an alternating lollipop. It has to be an alternating walk. So alternately matched and unmatched edges. So you enter this guy with a matched edge, take this unmatched edge, and leave with a matched edge. And so you're adding the 2 even levels plus this edge, and that's the tenacity of this edge. And similarly, the tenacity of a matched edge is odd level of u plus odd level of v plus 1. Okay, is that okay? So these green edges have tenacity 9, and in this picture, the green edges have tenacity 13, and these purple edges have tenacities of 15, and these yellow edges have tenacity of 17. Okay? This also shows you the nesting of these blossoms. I'll come to a definition of blossoms very soon. Okay, so what's the role of a bridge? So let's UV be a bridge of tenacity T, and I'm going to define its support to be all those vertices of the same tenacity as the tenacity of the bridge. Now that I've defined tenacity of an edge and vertex both, I can talk about both tenacities. It's the same tenacity that Swami mentioned at the beginning of the talk. So the support of this bridge is all those vertices W which have tenacity T, and there is a max level path to this vertex which contains this edge. Okay? And the point is, when you call double depth first search with this bridge, it should find the entire support by going down predecessors from both sides. Okay? And after having found the support, for each of these vertices W, their max level will be given as T minus the min level. Because min level plus max level is T, that being the tenacity of W. Okay, so for instance, this graph has 3 bridges, this green one, this purple one, and this yellow one. And the support of the green one is just these green vertices. And the support of the purple bridge is the purple vertices, and the yellow one is the yellow vertices, because the support is to be the same as the tenacity of the bridge itself, which are 13, 15, and 17. Is that okay? Okay, so that takes care of most of the things. No, half the things I want to say about the bridge. Half more are coming up later. So then let's go to base. And once we define base, we can define blossom. So let's take a vertex of tenacity T, where T is less than the length of the minimum length augmenting path in the graph. Okay? Because base is only defined for these vertices. When you have a vertex whose tenacity is exactly L or bigger than L, then it may not have a base. We don't need to define it. Okay? So for this vertex, let P be either a min level path or a max level path, and define HV with the H of V with respect to P, with respect to the path, to be the highest vertex of tenacity strictly bigger than T on the path. So we start from the unmatched vertex and look at the tenacities of all the vertices until we reach V. Of course, we started with the vertex of tenacity, either infinity or at least or L or more, so strictly bigger than T. So it's certainly bigger than T, and then somewhere we might encounter smaller than T or whatever. But look at the last vertex, which is bigger than T. Well, it could be this itself, but whatever it is, and mark it. So mark these on each of these paths. Okay, and look at the set of all the vertices you have marked. How big is this set? Any guess? This is a very special number. There's only one number which is very special in this context. 1. Turns out it is 1. So HVP is independent of P. That's the central theorem. Takes a fair amount of sweating to get to this theorem, and I'll justify all of that later towards the end of the talk. And that I'm going to define to be the base of this vertex, that unique vertex. And B is called a basal vertex. Whenever a vertex is a base of some other vertex, it's called a basal vertex. And of course, the tenacity of B is strictly bigger than the tenacity of V by definition, because we looked at the highest vertex of strictly higher tenacity. So it's strictly higher tenacity, so it is bigger than this. Okay, what's the significance of base? First of all, one thing that's obvious from the definition itself is base V is present on all even level V and odd level V paths. So like for this vertex V, this is the base. This is an even level V path. This is an odd level V path. And the base is always present, obviously. It comes from the previous slide. More importantly, let's define the even level of V with respect to B to be the shortest even length alternating path from V to B, starting with an unmatched edge. Okay, so what's the shortest even length path starting from base V to V, starting with an unmatched edge, not starting with a matched edge? Then this is 1, 2, 3, 4. That's even level of V with respect to B. Then the theorem is that this even level V path consists of an even level path to B, this one, followed by this even level path from B to V, the shortest even level path from B to V. Okay, so similarly for odd level, it will be the shortest path to B followed by the shortest path from base V to B, which is odd and starts with an unmatched edge. So so another way of saying it is that if I look at the even level B path, any even level B path, and any even level BV path, any, which has to start with an unmatched edge, then they meet only at B. So this even level BV path cannot go and hit this stem. It meets this path only at this one vertex. And so you take any one of those and any one of those and concatenate them, and you got an even level V path. Similarly, you get an odd level V path by taking the other thing. Is that reasonable? So in some sense, we can do divide and conquer here. We found the path up to base. From base, we found new paths. But I'm not going to do divide and conquer. But hi, Joseph. Oh, I should tell you this slide a little bit. Or should I repeat this? No. It will come up again. OK. So do you want any more illustration of this, or you buy this fact? OK, good. So now this vertex has this base. And what's the base of this vertex? Huh? First yellow guy. And the base of that vertex is this. So these are the iterated bases of V. Base, base square, and base cube. And notice that they all keep going up in tenacity, because the base of a vertex is higher tenacity than a vertex itself. Right? And this is all figure later. I mean, all of these are absolutely essential to pin down to give a correct proof of correctness of the algorithm. Okay, so now I'll give a completely graph theoretic definition of inner and outer. A vertex is inner if its even level is smaller than the odd level, and it's outer. It's outer if its even level is smaller than odd level, and it's inner if odd level is smaller than even level. So for example, these two vertices are outer because even level is 5 and odd level is 4 and odd level is 5, right? These two vertices are inner because their odd level is 3 and even level is bigger, okay? So what can be said about a base? Will it be an outer or an inner? Sorry? Yeah, base is always outer. So look, the even level is 2 and odd level is infinity. So base is always outer. Because we were looking at the highest vertex of higher tenacity. Turns out whenever you have a matched edge, the tenacities of the two vertices are the same. If you have an unmatched edge, the tenacities of the two vertices may not be the same. Like here, the tenacity is 9 here and infinity here. But these two have the same tenacity. So okay. So the point is that basal vertices are always outer. So the base of the green vertices is this outer vertex. The base of these purple vertices is this outer vertex, yellow. And the base of the yellow vertices is this outer vertex. Okay, so now we can come back and define blossoms from the perspective of minimum length paths. So blossoms give max levels to vertices, that we know. And they hide complexity just like Edmonds blossoms, because they contain all the shortest paths from the base to the vertices in the blossom, and I'll prove that. And but the point is that this is from the perspective of minimum length paths, and this is a purely graph theoretic definition, not an algorithmic definition. And here's finally is a definition of a blossom. So let B be an outer vertex, which has tenacity strictly bigger than T. Then the blossom with having base B and tenacity T. So blossoms always have two parameters, the base and the tenacity. The blossom of tenacity T and base B is, well, empty set if T happens to be 1. No vertex has tenacity 1 because, yeah. And now assume that we have already defined blossoms of tenacity T minus 2, up to T minus 2. Then the blossom of tenacity T with base B is, first take all those vertices of tenacity T which have this as the base, B as the base, and union it with all the smaller blossoms of tenacity T minus 2 sitting at all of these vertices and at the base. And that's the blossom of tenacity T and base B. So all the vertices whose tenacity is T and whose base is B, plus all the smaller blossoms of tenacity T minus 2, whose base is any one of these vertices or B itself. So let me show you tons of examples to make this definition clear-cut. And please feel free to ask any questions there. So what's the blossom of tenacity green and base this guy? The 4 green vertices, yeah. What's the blossom of tenacity yellow? Tenacity 15 and base this guy. So first of all, the set S will be these purple guys, and then on top of that you add all the small blossoms sitting on the purple guys or on this fellow. And on this purple guys it's a smaller blossom, so it's the green and the purple. And what's the blossom of tenacity 17 sitting on this base? It's all the yellow, purple, and green vertices. Let me ask one more question, and then I'll be happy to answer your question. So what's the blossom of tenacity 13 sitting on this base? This base. Empty. Good. Was that your question? No.
Even for the smallest tenacity, the blossom is a lot more complicated than a cycle.
Absolutely right on, and I'm going to show you that next. This is one blossom. Okay, bridges don't define blossoms, unlike what I might have said, and that was just to give you an approximate picture before we could go on to the real picture. Yeah, this is one blossom. This is not a base. Its tenacity is 11. The tenacity of a base is strictly higher. Okay, so you were right on. So blossom with this base and tenacity green is just the green guys, but the blossom with tenacity purple and this base is the purple and the green guys. Because because this guy sits on the base. Similarly here. These are sort of isomorphic but looking different. So blossom of tenacity green with this base is just the two green guys. Blossom of tenacity 11 with this base is the green and the purple. Because S is these two purple guys, and then you add the blossom which sits on the base. Yeah? And this is the blossom of tenacity green, and the blossom of tenacity purple on this base is purple and green. And notice that this is a bridge. Okay, this is not a predecessor of this. This is a predecessor of this. This is a predecessor of this. This is a predecessor of this because you go like this. This is a predecessor of this. So this is predecessor star of this, predecessor recursed. But this is not a predecessor of this, and this is a very strange bridge. It came very late in the picture when some counterexamples I was looking for, and this crashed some assertions that I thought were true, and then I got the correct assertions. Okay. So blossoms are well behaved in the sense that the set of all blossoms form a laminar family. And they hide complexity in the following sense, and this is where you can catch up with the slide that you missed. So let V be a vertex in this blossom, so its tenacity is at most T, obviously. And defining even level of V with respect to this base to be the shortest alternating path from B to V starting with an unmatched edge. And what I already proved was that gave you the statement of the theorem that every even level V path consists of an even level path to the base concatenated with an arbitrary even level path from B to V. And these two can be arbitrary. You just patch them together. They can only intersect at B. They cannot have any more intersections. And they'll give you a simple path from whatever unmatched vertex to V, and that will be the even level V path. And moreover, the second thing I want to state, the new thing I want to state, is that this entire path from B to V, even level path, is entirely inside the blossom, plus the base, of course. Okay? And the same for odd levels. So for instance, this is the even level path to this vertex. It consists of even level path to the base, followed by even level path from B to V. And this last part is completely contained in this blossom. So for example, what is the even level path to this vertex? Okay, its even level path goes like this. And this part of the path is completely contained in the purple blossom, sitting on this base. And you just concatenate that with the path, the even level path to this base, you got the even level path to this vertex. Yes, sir?
Maybe I missed something in the definition, but you said that like one of those blossoms is empty. Why is that?
The green one with this base, which, okay, what is the set S? Which is mainly, basically, which green vertices have this as the base? What is the base of these green vertices? Is this. So which green vertices have this as the base? None. So end of story.
Oh, I thought there was another union.
And what are the smaller blossoms sitting on this of tenacity less than green, strictly less than green? There's no vertex of strictly less than green anyway. Yeah, you're right that there was another thing also, but even that's empty. Yeah? But yeah, that was a nice point. Yeah, thank you. Okay, so we come to the algorithm finally. So here are the three ideas in the algorithm. Double defer search, which you saw last time. How to mark blossoms appropriately so all paths through them can be found very, very efficiently, all in linear time. So you examine each edge only once. That's it. And a third idea that I will talk about, which is kind of, has to be shown with some nice examples to make clear what it is. So So how to mark blossoms so paths can be found through them easily? So let me show you what happens from search level 4 onwards. We do search from along this edge and label this guy 5 and this guy 5, and we'll search along this edge and realize that this is a bridge. So we call double depth first search, and it finds this blossom. And actually, that's also a lie, and I'm correcting it right now, and I'll show you later that why it's a lie. This is called a petal. What Swami mentioned, petals and buds, is coming up right now. So a blossom is a union of certain number of petals. So this actually turns out to be a petal, and it'll become clearer in the next couple of slides. So it puts down here a petal node, which points to the base. All the petal nodes point to it, which are these 4, and this petal node points to the 2 endpoints of the bridge. One is red, one is blue. Remember red and blue trees yesterday? So in fact, there are red and blue depth first search trees with these 2 as the roots. Okay? And similarly, at search level 5, we search along this edge and realize, oh, it's a bridge. And we put on another petal node which points to the base. And all these vertices in the petal point to this guy. Of course, these earlier vertices are, these are all of tenacity 11. These were of tenacity 9. So the 9 don't point to this guy, only the tenacity 11 vertices point to this guy. And it points to the 2 endpoints of the bridge. One is red, one is blue. And now suppose we came in here. So we found an augmenting path from here, some path went off somewhere. And we want to find a path right through this petal and down like this, okay, when we actually find paths. So we want to find an even level path from here to the base. What we do is, because we are coming into an inner vertex, if we were coming into an outer vertex, we would come just down like that. But if we are coming into an inner vertex, then we have to go around the blossom, take the longer path. That involves jumping through this petal node to the 2 endpoints of the bridge, finding a blue path from here to here, and finding a red path from here to here, skipping over intermediate blossoms, which will be opened recursively. Okay, that's the whole algorithm for finding paths. When it so happens that we need to find a path, because we have an augmentation. So I'm using here these things that I talked about yesterday. There's a path from A, there's a red tree and a blue tree with these 2 as the roots, A and B, and there's a red path from A to each of the red vertices and to the base, and there's a blue path from B to each of the blue vertices and the base, and we'll always be finding a path from A to one of the vertices, maybe the red vertex, and from B to the base, or from B to one of the vertices and from A to the base, in order to find the long path through the blossom. If we are finding the short path, then we just go down predecessors and be done. Is that reasonable? Okay. So yeah, so I mentioned this point earlier, but let me re-hammer it in. Basically, double depth first search doesn't find blossoms, it finds petals and bridges, and as you said, blossom is more than what we saw. This whole thing is one blossom, and we could do double depth first search on these bridges in arbitrary order. If we do it first here, then we find this petal node, and later we find this petal node, and this guy points to that petal node, and so on. Okay? And at the end of this search level, you may have many more petals joining into this, and maybe this is also not the base. It is still just a bud. So this is a bud, it's not the base. Maybe this also is an unmatched vertex, but suppose there was more here, and this could be the bud. And the point is that bud of bud of bud of bud finally will be the base of all these vertices. Each of these vertices will have that guy as the base. The highest vertex of higher tenacity on all even level B and odd level B paths. And another point is that the union of all these petals, which have this as the bud star, will be the blossom of this base and that particular tenacity. Is that okay? Are you happy so far? Huh? Because I see you're understanding the whole thing. Yeah? Yeah, good, thank you. Yeah. It's great to hear, of course. Yeah.
You're running the double decimal search
On each bridge, to find its petal. So first one was on this bridge to find this petal. The second one was this to find this petal. And when we did this, we didn't come down these vertices because these are already in a petal. So this will come, from here we come down here, from here we go directly here, and then, so we never repeat those edges. Each edge has to be seen only once on each of these functions. Yeah. Yes, sir?
In the petal, like, you're hinting at a data structure which is gonna like compress things, right?
Sorry, it'll compress?
When you're drawing like those circles, it seems to me that you're hinting at like some data structure that's gonna compress the path. Is that what you're gonna do?
Later, yeah. We use path compression.
Okay,
Yeah. For not for anything that I've mentioned so far, but for another reason altogether. It's coming up. You'll see that. That's what I meant by we'll need some data structures also. Besides doing constant amount of work per edge, we'll also do some work order M using some data structures. Okay, so the main ideas were these three, and I've talked about this and this. So let me start talking about this. What is this precise synchronization of events, and what goes wrong if you don't have this the prescribed precise synchronization of events? And the synchronization of events is like this. So the whole phase of finding these shortest paths is organized into search levels, which start at search level 0. And at search level I, you look from those vertices who have a level of I. If I is even, then it's the even level. If I is odd, this is the odd level. So for instance, when I is 0, you look from the unmatched vertices, which have even level of 0. And when I is even, you look along unmatched edges incident at V. When I is odd, you look at the matched edge, the unique matched edge incident at V. And you assign a min level of I plus 1 to the other endpoint. If it is unassigned. If there was no label on it, then you have visited it for the first time and you assign it a min level of I plus 1. Okay? And once you are done with all of the vertices which have a level of I, to assign min levels of I plus 1, then you come to max. This is the second routine here inside the same search level. And here you pick up all the bridges of tenacity 2i plus 1, which are all sitting in some bucket. And for each one of them, you do a double defer search along to go down their predecessors, and you'll pick up all the vertices of tenacity 2i plus 1 and give them their max levels. One by one, in arbitrary order, all these bridges. Okay? So, again, our favorite picture. So, at search level 3, we find this edge and label it 4. At search level 4, we found this edge and we put it into the bucket of bridges of tenacity. 9. And then once we are done with min, we look at we are in search level 4. We look at all the bridges of tenacity 9, because that's 2 times 4 plus 1, namely this bridge, and do double defer search on that, and we find these 4 vertices. And give them their max levels. Yeah? Is that okay, Joseph? So, and we assign to these guys their max levels of 2i plus 1 minus the min level. So, the question is, will this scheme work? What will be the proof? What is needed to complete the proof? Because I'm not even giving you all the statements that are needed to complete the proof that this scheme will work as given here. I mean, there's a lot of things going on here. IAs and I plus 1s and bridges and props and min levels and max levels. and then you go to the next search level and the next search level, and have you done everything properly so far, and is everything set up in the right way to do everything right from here on? I mean, there's a lot to be said here. And so let me just quickly say what needs to be said to show that it all works. So of course, to show that this all works, we'll have to do an induction on I. And so min level is assigned by a predecessor. So min level of V is assigned by a predecessor. And that's right next to V, right? It's a neighbor of V, which has one level of if you have to give a min level of I plus 1 to V, there must be a predecessor who has a level of I, whatever is the parity of I and I plus 1, right? There must be such a thing, and that guy gives it to V a level of I plus 1, okay? And of course, if I is the min level of V, we have found it by induction hypothesis. What if I is the max level of V? Then the tenacity of U, sorry. What if I is not the min level of U, but the max level of U? And then from U, you searched along some edge, and you got to V and gave it a min level of I plus 1. How do you know that its max level has been found? Because if its max level is I, its min level is I minus 1 or less. So its tenacity is less than or equal to 2I minus 1, which is 2 times I minus 1 minus 1. So this max level would have been found by the previous search level in search level of I minus 1. Therefore, this has also been assigned. So if I is the min level of U, it's been assigned by one argument. If it's a max level of U, it's been assigned by another argument. It's been assigned anyway. And so therefore, searching out from U, you will assign min level to V. Okay. What about max? So the max level is assigned by a bridge, which is not a neighbor of V. It could be very, very far away. Depending on how big that blossom is, it could be, huge. So how do we know that there is such a bridge out there? And what does it mean, such a bridge, which will assign V its max level? And how do we know that it will be found on time in respecting all the rules of the previously stated algorithm? How do we know that will happen, right? That's what was the big question in my mind in 1989 when I started laying out this structure and just gave a bare-bone idea of this structure without correct proofs, but they are now correct, fortunately. So what does this such a bridge mean? Okay, so remember I defined the support of a bridge to be all those vertices which have tenacity T, and there's a max level path to them containing this bridge. So again, I mean, I don't know if we need to go into this example again, but there are these 3 bridges and their supports are green, purple, and yellow vertices. What we must show is that if V has tenacity T, then V is in a bridge of support, is in the support of a bridge of tenacity T. That's what we must show, right? Who will give it its max level? Only a bridge of tenacity T in whose support V is. What does it mean that V is in the support of that bridge? There's a max level path to V which contains that bridge. And in effect, we will end up showing the following theorem. So let V have tenacity T and P be a max level V path, then there's a unique bridge of tenacity T on P. So we have to show that every max level path to V has a bridge of tenacity T on it. And so if V has a max level path, it has a bridge of that tenacity. When you do double depth of search on that bridge of that tenacity, you will find V and give it its max level, QED, right? And this turns out to be what? This is a purely graph theoretic fact. Every max level V path has a bridge of tenacity T on it. we cannot prove this algorithmically. It's a graph theoretic fact. And that's why we need all those graph theoretic facts, including a graph theoretic definition of blossoms. Those facts go very much into proving this theorem. Okay? Is that all? So once we prove this fact, we are still left with proving that this bridge will be found in time, so that double depth first search will do the right thing and label V with T minus its min level as the max level. Okay, so going back to the scheme, we need to show that after min is done here, whatever bridges we have accumulated of tenacity T plus 1 are indeed all the bridges of tenacity T plus 1. There are no other bridges of tenacity T plus 1. Some of them are accumulated during min. Some of them may have been accumulated in previous search levels. And I'll show you that also. But altogether, they must be all accumulated by the time min is over with, so that when you come here and you do double depth first search on all these bridges, every vertex that needed, every vertex of tenacity 2i plus 1 gets its max level once you're done with max. Okay, and that will be a complete proof by induction. I think you have a question, right? You're thinking deeply. Yeah? No? Okay. So, to prove this fact, actually, there are a few subtle things going on, and one of them is the following. Remember I told you that in the case of bipartite graphs, this edge which goes from a higher level to a lower level is not going to be useful, because this will be a longer path than this one, right? So we got rid of this edge. And I had said that this edge will be useful in general graphs, which goes from a higher level to a lower level. Why? So let me show you that. So suppose at search level 4, we'll search along this edge, and we found this unmatched edge from here, going from higher level to lower level. In the bipartite case, we could have thrown it out. Here we cannot, because it's called an anomalous bridge, and it could be useful once this blossom is closed. Or even useful like this, to give max levels to all these vertices. Okay? So, and I call it an anomalous bridge because its tenacity is not known at the time of its discovery. Because when we search along this edge, this guy only had an odd level, not an even level. But the tenacity of this edge is even plus 1. And its even level will come about when this bridge is found and double depth first search is done there. And at that point, we will give it a max level of 8. And then we know the tenacity of this bridge, namely 13. And we put it in the right bucket, bucket number 6, I equal to 6, search level of 6, because 2 times 6 plus 1 is 13. Okay? So its tenacity is 13, and we put it in the correct bucket, and then we pick it out of that bucket and do double depth search. But the following question arises. So we'll do double depth search on this bridge at search level 6. But we know it's, and at that point we'll give these 10s and these 11s and these 12s to these vertices, max levels. But we know its tenacity, that this is a bridge of tenacity 13 at search level 5 itself. Okay? Why should we wait till search level 6 to do double depth first search on it? Why can't we just do double depth first search on it at search level 5? What could go wrong? Yeah?
Another tenacity 11 bridge could interfere first.
Good. Yeah. Because okay. So let me go exactly that thought. Fantastic. Thank you. And let me give you an extended example to show what will go wrong if you happen to do double defer search out of turn. You know it's tenacity, you know it's a bridge, but its double defer search should have been done at a certain other search level. So let's look at this example, which will clarify things completely. Exactly what she said. So this has tenacity 11, and at search level 6, so this bridge of tenacity 11 is found and is processed, and this at search level 5, we found this edge and we found this edge, and we processed this bridge and we gave this guy its max level. At search level 6, we found this edge. It is not an anomalous bridge, even though it goes from high to low, because in the anomalous case, I've defined it to be that in which you do not know its tenacity at the time of finding the bridge. But here we know this tenacity, which is 6 plus 8 plus 1, which is 15. Okay? So this bridge of tenacity 15 has been found. Its double defer search should be done at search level of 15 minus 1 over 2, which is 7. So not at search level 6, but at 7. But suppose we say, hey, we found the bridge, we know its tenacity, let's do double defer search. What will happen? Well, in this case, we'll do the right thing. We'll give a tenacity of 15 to all of these vertices, and their max level will be 15 minus the min level. But suppose, as she said, there was another bridge of tenacity 13, which is also happy to give max levels to these guys, okay? And it has to be processed at search level 6. So if we process this, and suppose we put this and this both in the bucket and happen to process this first, we'll give this guy's tenacity 15, which is wrong because their tenacity is really 13 coming from this bridge. And all of this will be in a petal, so when we do process this bridge, we'll jump directly to the base. We'll not even encounter these vertices. They've already obtained their max levels and their tenacities. And that's all critical. This whole thing is critical for maintaining the running time of one edge, one constant number of operations per edge. Because when we do double defer search here, and if we had encountered some vertices which do not have a max level and a tenacity yet, we can be sure that this is the right tenacity. We don't have to look around all over the world to see, oh, is this 15 or 13? If it were 13, that should have been done already. And if you encountered it now, there was no 13 there. 15 is correct. Okay? So that's the point, that the prerequisite is that all lower tenacity vertices should be labeled and be already in blossoms so that whenever you encounter a fresh vertex, which doesn't have a max level, you know what its correct max level is. You cannot spend any more time looking around to see to confirm its max level. You know it is what it is. Okay? And so that's what I mean by precise synchronization of events. Okay, and then remember I said that there are bridges that have empty support, like these. This has tenacity 17. When you do double defer search, before you do double defer search, you don't know that it has empty support. But when you do, you'll go from both of these endpoints to this guy, or in this case, from these two endpoints to this guy, jump directly to one place, and then you know that there is no support on these. There are no more max level guys to be found, right? And these may be most of the bridges, actually, even though in my figures they are not there because they are useless. Okay, so one last thing that you said about data structures. So we are coming down this path, and we are coming down these pointers into the petal node and to the base, and into the petal node and into the base. And we could be taking a very long chain of these pointers. Okay, who's going to pay for that? There's only one edge here, which led to this whole pointer chase. We cannot charge all of this work to this edge. I said there'll only be a constant amount of work charged to one edge. Which edge will pay for all of this work? So it turns out we need the union find data structure. And if you are on a pointer machine, it will add another alpha factor to the running time. Alpha is inverse of Ackermann function, which is for the number of atoms in this universe might be at most 4 or some such thing. Something that grows very, very, very slowly. It's a primitive recursive function. Oh, no, it's not a primitive recursive function, sorry. Alpha, yeah. And, but on a RAM, this issue has also been taken care of, and it's all linear time. And RAM is the standard model for computation. So that's why the running time is really linear per phase. But there are 2 ways described in my paper to get rid of this alpha because of the structure of petals and buds and all that. But these are difficult questions, and who has the time to get rid of an alpha factor which is already 4 anyway? So, but if you do, feel free to answer those 2 questions. One of those 2 should give an answer. I don't know, but there are 2 ways out suggested in the paper. So what will happen as the result of this is, this needs a RAM model, this is a pointer model, then this will be order m time in a pointer model as well. So that's the academic improvement. Yes, sir?
For the version that needs the RAM model, is that the algorithm where you need to know the union structure in advance?
You have to read this paper. You maintain a lookup table of some kind. You use the fact that the RAM word is log n bits long. And you use all of those log n bits to do some table lookup and all kinds of other things. If you wanted to implement this algorithm, you wouldn't do this at all. You would do this, because this is only 4 or 5 anyway. Yeah. And it's a very simple algorithm. This is very complicated. It's just academic interest. Okay, so there are 3 tasks needed for non-bipartite matching also, which is first is to do the forward search to find min levels and max levels. The other is to find augmenting paths, and then to erase judiciously. So let me tell you a bit about finding the augmenting path. So suppose we did double depth search on this bridge, and we found these 2 vertices in the lowest level. So we know there's a path from here to here. So we come back here, and we know we have entered an inner vertex, so we need a long path through this blossom. So we jump to the 2 endpoints of the bridge and find, say, a red path from here to here and a blue path from here to here. I already talked about it, and that kind of a thing is needed. I'm just repeating myself here. This is an important step where blossoms actually, all that marking is actually used. And then we have to erase, once we find an augmenting path, we erase it. We erase all vertices recursively which don't have any predecessors, so that the picture is left as it was when we found the first augmenting path. So everything should be as intact, meaning so that we can find the second path and the third path and so on. But what does that mean, that the picture is as intact as when we found the first path? In particular, how are we sure that we won't have half-eaten blossoms left behind? Okay, maybe this first path ate through some part of a blossom, and now whatever is left behind, we didn't erase it all because maybe when we erased predecessors, this didn't get erased, and now we cannot find a path through that, and we do all kinds of work to get to it, and that's wasted, right? But that cannot happen, because if any vertex is in this blossom, then the base of this blossom is a pred star of that, pred of pred of pred of that. So this vertex will be erased sooner in the erase phase. Okay, so where pred is the reflexive transitive closure of predecessor. So if B is removed, the whole blossom is removed. Moreover, if P is any even level B or odd level B path, then all the iterated bases occur on the path. And even a vertex U that lies on it, even all its iterated bases occur on this path, even if it is breadth for such dishonest on P. And I'll say more about this in a moment. So basically, all of these iterated bases are being on the path means they are all removed, so that whole big blossom is removed. So the picture is as clean as when you did the first path, when you found the first path. All those markings are around to find the second path. Okay? So finally, I want to say this. Remember, I started by saying that that the big problem is that paths are not best first search honest, and it could be an exponential time algorithm. And I said that the structure of matchings limits the breadth first search dishonesty quite intensely, okay? And let me tell you explicit theorems that limit the breadth first search dishonesty. The first theorem is that if P is any even level B or odd level B path, and U lies on the path and its tenacity is at least as high as that of P, as large as that of P, then U will be breadth first search honest on the path. So in other words, the only vertices that will be dishonest are lower tenacity vertices because they are on smaller blossoms. Okay? Secondly, so as a corollary of this, all these iterated bases will be breadth first search honest on the path because they are higher and higher tenacity than V. So base V has higher tenacity than V, base square has higher tenacity than base V, and so on. So they all will be breadth first search honest on the path. Second, suppose U lies on this path, but is not breadth first search honest on this path. Still, what I can show you is that all the iterated bases of U lie on the path, and U is honest with respect to its base, and for the rest of the bases, base k is honest with respect to base k plus 1. Okay? And the final biggest base is honest on the path itself. And this needs an illustration. So let me show you what's happening here. Do you get that? I mean, so even the vertices which are not breadth first search honest, their bases lie on P, and there is some honesty between one base and the next base. So between k and k plus 1, between U and base U, between base U and base square U, between base square U and base cube U. Okay? And that's what is needed because when you find those paths, you go from one base to the other, to the other, to the other, and you know, eventually when you find the paths, you open the blossoms and you go, yeah, so that's all available, all that structure. So remember this beautiful picture that I asked you whether the even level of V is finite, and it was a little hard to get the path because the direct path to U, the shortest even level U path, blocks all paths to V. Okay? But if you take a longer path to U, namely this one, then you can find a path to V. So U is dishonest on this green path. Its base is also dishonest on the green path. But U is honest with respect to the base on the green path. And the base is honest with respect to the base square. And the base square is honest with respect to base cube. And that's what I was trying to say. And I said, you know, this path has to be found. So we have to understand the nesting of blossoms here. And the nesting is that this blossom with this base is contained in this blossom with this base, which is contained in this blossom with this bridge and this base. And by jumping to the endpoints and finding those paths, exactly as I said, nothing more than exactly what was needed there. Even though it's so complex and put together like this, it'll all work out. And so why did the proof take so long? Okay, because look at what's needed. In order to define a blossom, we first have to define the base, obviously. But to define a base, we have to show that this HV, sorry, not BV, HV, that set is a singleton. Remember I asked how big is that set? It's a singleton. And to show that, we need to define blossoms and its properties, that all these even level BB paths are inside the blossom and all that. All of that goes to show these things. So there's a massive chicken and egg problem. And this I didn't even realize the first time I gave a proof, which came in Combinatorica of all places, which is the flagship journal of matching in some sense, full of errors. But now, fortunately, everything is cleaned out. And in fact, I challenge you to prove this theorem. As such, the only way I know to prove this theorem is to prove all the facts that I've stated so far simultaneously via an induction on tenacity. So prove all of those facts for smallest tenacity, then for tenacity that plus 2, then that plus 2, and so on by an induction. And the other thing is that the big breakthrough idea that came only, I don't know, 2 years ago, something like that, was that the power of double depth first search was needed not only in the algorithm, but also to prove these facts. Because in the first paper, I was proving these facts by following single paths, and graph theory, as I told you, it's immensely complicated. If you have to argue about single paths that are like a spaghetti, it's impossible to argue about them. But by using the properties of double depth first search, I got a disciplined way of asserting very high-level facts, which gave rise to these clean proofs. Okay. And moreover, the clean proofs were done not in the original graph, but in graphs derived from the original graph, which are these layered graphs where I showed you the double depth first search, where it was easy to ascertain facts and prove things. Okay, so finally, I want to say that this is the main algorithm. And you can stare at it and see how simple it is. Right? You just iterate on the search level, you assign min levels, you assign max levels, and you have to, of course, prove quite a few things, and that takes work. But the algorithm is trivially simple. Well, not trivially, but it is simple, right? And that's the way it should be, right? The algorithm has to be easy. The proof could be arbitrarily hard. And finally, I just want to state this result, which shows that for bipartite graph, cardinality matching has gone all the way to pretty much close to linear time. MV algorithm has practical value because there's no hidden constants anywhere, especially if union find you use Tarjan's union find rather than this Gabo Tarjan. There's no hidden anything. It's all linear time, other than that alpha factor, which anyway is tiny. So I'll leave you with this blossom.